Hey guys, in this video I quickly want to iterate what we talked about in today's class. So we wrote down some of these equations on the board, but I just want to make sure everybody understood what we talked about in terms of the equations and the terms involved. So today we talked about aerostatics a little bit more in terms of aerostatics is just a study of gases that are not in motion. Um, so aerodynamics is the study of gases which are in motion, which we will talk about too in class. But again, the main important equation of aerostatics is also equation state for ideal gas. That's PV equals nRT. And again, we really want to write that ideal gas equation in terms of density and without having the volume and number of moles and all that. So we can do that by writing volume in terms of density and mass using this formula where density equals mass by volume, and mass equals N here is the number of moles, and the capital M is molar mass. So I wrote down all the parameters and what they represent here. So please go and check it out. Again, you're more than welcome to use these equations. Just copy and paste it in your portfolio. Right. So when you do this substitution, you can cancel the mass, and in the end, you will get P by rho equals R by T by M. So you got to know that this R is a universal gas constant, and R by M is what is called a specific gas constant. So again, that's why we were able to cancel R's when we equate the pressures inside and outside the balloon. All right, let's move on to making an assumption that in a helium balloon, the pressure inside equals to the pressure outside the balloon. Again, this is quite not true. The pressure inside the balloon will be slightly higher than the pressure outside because it has to hold its shape. But for simplification assumptions, in a simplification, you can assume P1 equals P2, right? That means P1 is, in pressure inside the helium balloon is rho1 R T1 by M1, and pressure outside is P2 is rho2 R T2 by M2, right? So we equate these two pressures and come up with a relation for density, right? Rho2 by rho1 is the ratio of molar mass times the temperature ratio, and the R's will get canceled because it's a universal gas constant. Right, so this is kind of the equation we derived in class, okay? Now, to understand how this equation can help us predict the lift created by helium and hot air balloon, we got to look at the Archimedes principle, right? What he said was, if you do the force body diagram, right, the buoyancy force experienced by any object immersed in a fluid is equal to the weight of the object, weight of the fluid that the object displaces, right? So that's FB buoyancy force, right? And we have minus weight of the helium acting down, weight of the structure acting down, weight of the payload acting down, right? So let's assume for now that there's no structure and payload, which means that your lift will just simply be density times volume, which is mass, and times gravity, which is the weight of the fluid, which is air displaced by this balloon being in the fluid, right? Minus rho1 Vg, which is the weight of the fluid inside the helium balloon itself. Okay, so with some groupings, right, you can take rho2 as common, which is rho2 is air right here, right? And you can write as rho2 Vg 1 minus rho1 by rho2. Okay, that's great, but if you look at here, the formula we just derived from the equation of state, we can write rho2 by rho1 as m2 by m1 times t1 by t2. Now, if you assume constant temperature inside and outside the helium balloon, then you can just write rho1 and rho1 by rho2 as m1 by m2, right? So again, we saw this equation in class, right? But what we didn't do was, I didn't note down what the molar masses for helium and air was, so I kind of put it right here. So the molar mass for helium is 4 gram per mole, and molar mass for air is 28.97 gram per mole. So let's put this into the equation, right? So when you put this into the equation and simplify it in terms of ratio, you will get rho2 V2G. Again, rho2 Vg is the weight of the fluid that you're displacing, right? Times 6 over 7. Let's look at what this represents, right? If you get 7 over 7, which is 1, that will be the maximum lift attainable. Do you guys understand that? That means that if you have a complete pure vacuum inside the balloon, then you will have 7 over 7 because there will be no mass inside, right? So you are actually getting 6:7 ratio, right? Which means that's kind of what I said in class. About 85% of the volume of the weight that you displace by the balloon is termed as lift, right? So with helium, you get 86% of the weight you replace as the lift force, which is actually pretty cool. Again, you're not doing much work here, right? You just have to generate helium and then pump it up into the balloon. Okay. Now let's look at the hot air balloon, for instance, right? So we still have this equation of state, and we look at the Archimedes principle here, which is buoyancy force and minus the weight using force body diagram. But instead of having weight of the helium inside the air inside the balloon, you have hot air inside the balloon, right? So let's also go ahead and assume there's no structure and no payload. So that means we have this equation right here, rho 2 Vg, which is weight that is displaced by the balloon, and also the weight of the air inside the balloon, right? And this is the equation we had before as well. So now we have to write in terms of temperatures, right? Again, now you're making an assumption that the molar masses inside and outside are the same. It is just air, right? So this will go away, and you will just have the temperature ratio, right? So rho 1 by rho 2 equals T2 by T1, right? And T2 being the temperature, the ambient temperature, T1 being the temperature inside, right? So what you need to do is you need to heat the temperature inside the balloon greater than the temperature outside, right? So you can write that as T2 by T2, or T2 divided by T2 plus delta T, right? Now, if you do some arithmetic here, right, you take least common multiple and then you subtract the T2 in the numerator, and then you will get delta T by T2 plus delta T, right? This is the increment in temperature that you add to the free stream temperature or to the ambient temperature, right? So in the previous slide, we saw that the density ratio provided by helium was 6 over 7, right? So if you want to generate the same lift as helium balloon does, then we gotta equate, this ratio, right? Because this is what the right-hand side of the equation where the helium balloon gives us, all right? So let's do some math here, right? Delta T by T2 plus delta T equals, you do some arithmetic, and then you end up getting this term right here, that delta T equals 6 times the ambient temperature. Now think about it, right? In order to generate the same lift as the helium balloon, you got to increase the temperature of air 6 times more, right? So if you assume the air temperature as 300 Kelvin, right, 6 times 300 Kelvin will be 1800 Kelvin, which will be around 1526 degrees Celsius. Now, if you try to heat the air up to this temperature, you simply burn the balloon, right? So it's just not possible. Again, to create the same amount of lift as helium balloon, the hot air balloon must need to heat the air up to 1800 Kelvin, right? So in terms of efficiency, I would say helium balloon will be more efficient when compared to hot air balloon, because you're not doing much work, you're not burning fuel, but at the same time that the helium balloons, it's the material that you use to helium balloon is very, very soft and very thin. It's prone to rupture, and in order to generate vast amounts of helium, it's not that easy, right? Because helium being a light air as it is, any helium that is generated that's here on the ground will just simply rise up, right? Because it's a light air. That's what it does, right? So it's hard to get helium production that lot. So I just want to let you guys know that here is a valid proof using equation and the actual numbers. And we kind of saw the equations in class. We didn't get to see the numbers, but here you actually saw the numbers now. So if you have any questions, please feel free to ask in the next class on Tuesday, right? So, all right, now go back and read my reflections. Thanks.